All right. So, what is an algorithm? A lot of people have heard in recent news this word. Oh my God. Algorithm, right? A funny story is when I was a kid, I did not know what an algorithm was. And I always got the word confused with logarithm. Right? They kind of look the same. They have the same letters, right? It's basically you just swap the A and the L and the O and the same word, right? So it's like a logarithm algorithm. It's probably the same thing, right? Well, it's not the same thing at all. A logarithm is a function in math. It's more specifically the function that is the inverse of exponential. So if you have exponential function of e of x, right? The inverse of this is log of x, right? And the inverse is that if you multiply, well, if you compose them, you get the identity. But algorithm is something entirely different. So logarithm is a function in math. Algorithm is not a function in math. Algorithm is a word that means either lots of things or nothing. And nowadays you've heard it when you say, oh, it's the YouTube algorithm, right? Or it's the recommendation algorithm, right? Recommendation algorithm. And those instances of the word mean there is a process that a computer executes that does something, but we don't exactly know what exactly, like we don't exactly how it works. It's just a process done by a computer. That's what they usually mean. So those are particularly bad because usually those are machine learning models, and machine learning models are extremely different from algorithms. So what is an algorithm? So an algorithm is it's not machine learning, right? So it's not those things. It is a way. So okay, let's start with programming. In programming, an algorithm is just a program, right? So for programmers or coders or developers, an algorithm is just another word for program. Now the difference is you don't say usually, oh, I study programming. You say, oh, I have a course on algorithms. So what is a course on algorithms? So the reason we have programming and programs instead of algorithm is that we usually study, we study algorithms. That's why we mention, well, that's why we use algorithms in this context, the context of studying how programs behave. And it's more specific than that. It's study how a program executes its instructions in order to reach a goal. So when you talk about this, you have a very important question is the execution context. So I said to begin with, we're going to start with programmers. What is an algorithm for programmers? What is an algorithm in general? How does an algorithm manifest in general? It's a description of steps that you use in order to accomplish a task. So for example, if you're doing if you're sorting out papers, if you're doing your paperwork and sorting them by date, you probably have multiple stacks all in front of you, and you take the paper and you put the paper in the right stack, right? So for example, you have all your paperwork from the last 5 years, so you have a stack for each year, and you go through it, and you're like, you get a paper, and like, oh, this is 2016, I'm gonna put it here. Another one, 2018, goes here. This from last month goes in the last one, right? And so you take it and you look at it, and then you put it, and then at the end you probably compile each, you probably look at each one of the piles, and then you sort them through chronological order. So then you take the first pile, look at the first result, and say, is it from January, February, March, etc. If it's old, I will put it here. If it's new, I will put it at the back of the pile and go through it until I've gone through the whole pile. So this is an algorithm because you're executing steps in order to achieve a task, and the goal of the task is sort through the paper. So in this case, the execution context, I'm going to write this down, algorithm, let's say, well, it's not a sequence, it's a description of steps, description of steps to achieve a task or goal. So the execution context in this example is the world, like the real world, is taking paper, reading out the ink on the paper, and putting paper down. This is the execution context. Whereas for programs, the execution context is instructions, like programming instructions, each line, each operation, and how those are converted into machine code. And so the example that is used very often is recipes. Recipes, I think we already used this example, are like programs. You have steps, and then you go through the steps and you do it, right? So it's also, since it's a program, it's also an algorithm, right? Because you go through each step and you execute each step, and at the end the goal or the task is make a cake or make dinner. Now, when we say we want to study algorithms instead of studying just programs in general, what we mean by study is we want to extract and understand the relevant component that make up algorithms. And the relevant and common elements in algorithms are what is called complexity, which is a fancy word for saying, does it take a long time? Or does it take a lot of space on my desk to sort out paper? Is there a way that I can sort through my paperwork using less desk space? Or is there a way I can do it in less steps? So complexity is the study of how hard or how effective is the algorithm. And then there is patterns. So imagine we have two problems, and they seem unrelated. And there's notice on my headset. They seem unrelated. And the first problem is really hard to solve. But the second problem is really easy to solve. We have an algorithm, it's really efficient. Is there a way to understand the hard problem in terms of the easy one? Or can we reuse the same strategy from the easy one with the harder one, such that the harder one becomes easy? So complexity usually translates into big O notation and stuff like that. Big O, space, space, P, and P, etc. And patterns manifest themselves with things like divide and conquer, dynamic programming, etc. And there is one more thing I want to mention, and that's we haven't given a formal definition. I don't think I have a formal definition. I'm just gonna, okay, let's look up Wikipedia. Algorithm. So here's the formal definition I can give. An algorithm formally is, okay, yeah, I have one. It's an expression in a computational language. And what that means is not all languages are computational, right? So if you take an expression in English, English is not a computational language. You can't compute things with English. Likewise, you could have, for example, I was thinking, okay, a funny example of this is if you take a game of Magic the Gathering, the state of the game is like an algorithm because it represents a computation, and you can think about it in terms of how it executes, because each card has an effect, and each effect stacks on the stack. So you gather every effect of every card, then you put them in the stack, and then you resolve the stack effect by effect, which changes the state of the game, which might again add stuff on the stack, etc. You have a way of computing a result from this description, from this expression, from this state, from this original value that you have at the beginning. So you can't compute with English, but you can compute with Magic the Gathering. How does this translate with programming languages? So every programming language, if it wants to be useful, is computational because you can run it into your machine. And I say useful in the sense that if you want to write programs, like if you want to run Pac-Man, if your programming language is Pac-Man complete, then it's computational. So people might ask, well, there is something like, there's this thing called functional programming, right? And there's things like Turing machines. Like surely algorithms don't exactly mean the same thing in those languages, right? Because you can't go from one to the other, but it's not the same, and you don't write the same programs the same way, and they don't have the same performance. And since algorithm is all about complexity and understanding performance, how come we can understand both? And that's true in the sense that they are not entirely equivalent in those regards, right? You can't write the same algorithm in one language and in another, but they all have operational semantics. They all have ways of executing their programs. So for example, someone, I don't remember who actually, but was it Church? Was it Church? Alonzo Church? Let's say it was Alonzo Church. I'm not sure, I remember. Proved that lambda calculus and Turing machines are equivalent in the sense that they both have the same computational power. Everything that can compute with a Turing machine, you can compute with a lambda calculus. Now the difference between those is the Turing machine executes by reading off a tape, right? The head, it reads the head, and then it does something, and then either it writes something back and then it moves, or it writes nothing and then it moves, or it writes and it doesn't move, etc. It has a whole bunch of behaviors that are really easy to track by looking at the state of the tape. So every step in this case is every move or every read from the tape is a step. And so you can measure how many steps a program takes if you express it as a Turing machine by just looking at how often the head moves and does stuff, right? So each action could be a step, like reading, writing, moving, and then you count those. And then you have the amount of steps for a program. But lambda calculus doesn't have a tape, right? It doesn't have something that moves and something that writes and something that reads. So how does it do it? Like, what is a step? So in lambda calculus, a step is a reduction of an expression. So if you have, I don't know, if you have lambda x, what's a good lambda x, lambda y, and lambda z. Oh, I got a text message. And what you do is you return x, and you apply this to k. Well, the first step is executing, like replacing, like putting this k inside this this expression, right? So you replace x by k, and then you have this lambda y, lambda z, k. Then you can apply this to something else, which will pop the new y, and you end up with lambda z, k, right? And then you can apply this another time with something else, and that will remove k, and you end up with k, right? Remove z, and you end up with k. So here we can say, like, each application here is one step. So every time we reduce our expression, we count this as a step. So this is, for example, this program requires 3 steps to run. So that's how you would do it with lambda calculus. If we take magic, for example, what is a step in magic? So there's many ways of doing this. So for example, here we said every application is a step. We could have said every application and every replacement is a step. So for example, if I were to have x and x here, I would have to replace x twice, and that would be k and k. That would be 2 steps. That's entirely arbitrary. And most of the time, the way complexity study works, we ignore those things that we find irrelevant or not hard enough to count as a step. So for magic, for example, what we could count as a step of execution is apply the effect of a card on the board state. So every time you read a card and you apply its effect, that's 1 step. So given a board state, you have a card that, imagine the board state is empty, a card that says for 3 red, draw a card. It's really expensive, but that's fine. Oh, that's fine. 3 red, draw a card. That's costs, like the computational powers, this is 1. But if you have an enchantment that says, or every time a player plays a red card, duplicates its effect for you, and that's an enchantment that the opponent has, well, suddenly this has cost 2, right? It costs you trigger 2 effects by playing the card, right? By changing the program, aka by changing the board state, you change the complexity of the program, and so executing the program becomes harder because it requires more steps. So for magic would be, for example, the amount of cards you have to apply on the board to resolve all the effects. So we know, so I've explored what is an algorithm, why it's important that we talk about the execution context. Why is this useful at all? Why are people learning this in school, and why are people teaching this in school? And there are, much like there are 2 like two ways of studying it, those are the two ways that actually are useful. It's not for, like, we don't only teach people to understand complexity and patterns, but the goal is to make people think about the efficiency in their program and give them a common language to talk about the efficiency of their programs. So it's about not just programs, but it's also about how to approach analyzing program. So the goals of such a course would be, learn how to analyze programs, learn a common vocabulary, I want to say, to talk about performance, and learn how to, I want to say how to identify common problems, but that's not exactly right. Like, you don't learn to identify things. That's just pattern matching. But the goal is more to nourish an intuition for detecting what I want to say is you have two problems, and you should be able to say, oh, this problem is the simpler version of this other problem. Or I have this thing, it looks ugly and disgusting, but I can take it apart and use this other strategy that I used before to fix, to solve at least some parts of it. So it's about like taking things apart and understanding like each part might be similar despite its appearances. What's a good word for this? Let's say it's about how to. Oh my god, I can't find it. Understand? It's not understand. It's like piercing through. Let's just pierce through appearances. And this makes no sense unless you've watched the video. But really, like, have an algorithm be able to say, yes, this is unlike anything I've seen before, but this small part here is. And so I can take it out and solve it, and that will help me solve the whole problem. All right. Oh, we're doing really great. Okay. Let's go with some examples. So we've already mentioned the cake as an example of a program, and also as an example of an algorithm, because algorithms are just programs. It's not very interesting because there is not a lot to say about its complexity. Its complexity is always the same because the recipe has always the same amount of steps. You can sometimes merge some steps or skip some steps, but that's not the kind of gain that we want to see when we talk about complexity. So let's see a very typical example of a problem that we want to solve. This is bigger. Imagine that the problem we want to solve is as follows. Return the sum of every number from 0 from 0 up to an upper bound. I'm going to call it x. So create a program or a description in a computational language that gives me this result. So let's take again the example of doing it in the real world as a computational language. Our description could be this description English, that's fine. Our algorithm will be, well, I'm going to take a sheet of paper and I'm going to write down the previous number, the number I'm at. Oh, actually, no, I'm going to write down all the numbers from 0 up to the thing. And then at the beginning, I'm going to write 0, then add the next number beside it. And then sum the two. So here's the thing. So if I want all the numbers up to 5, I do 0, 1, 2, 3, 4, 5. And my algorithm is take 0, take this number, and then do plus, and that's 1, right? And now take this number and 1 and do plus, and that's 3, right? And then take this number, take this one, and plus, and that's 6, right? And then etc. 4 plus 6 is 10. 5 plus 10 is 15. That's my algorithm. I have an instruction. First instruction is write down all the numbers. The second instruction is write a 0 at the top. And third one is go down the list, adding the next number to the one that is just above it. That's the algorithm. And this takes as many steps as there is numbers, plus 2. Well, if you count a step as writing something down the paper, there is this amount of steps, which is 1, 2, 3, 4, 5, 6, 12. There's 12 steps. 12 steps to get to the upper bound 5. Let's say here x equal 5, and we're gonna do, so the manual version took 12 steps. All right, let's go now with the mathematical version. So the way you usually do that in math or with mathematical notation is you just say, say manual. So with basic math notation, you would say something like f of x equals the sum of I equals 0 to x of I, right? And so if x equals 5, then you have this expression here. Oops. 5 of I. But math doesn't really have a way to compute things, right? So this is not really helpful because math is not a computational language either. Now, if you write this as a program in like C or Python or JavaScript, like a imperative program, imperative, you might write something like for I in 0 to x, and then you do something like var sum equals 0, and you do sum equals sum plus I, return sum. So again, I have an expression in a computational language, I have a way of executing this thing. And let's say that every going through a line is a step. So you go through this line, that's once. Then you go through here, that's 2. Then you go here, that's 3. Then you go here, that's 4. But that's not quite right, because this thing here, like this part here, is executed x times, right? And x is 5. So this is actually yeah, this is actually 5 steps. This line here. So we actually have 1, 2, then 5, that's 7, 8 steps. So I'm gonna write program here. And I'm gonna put 8. And just for funsies, I'm gonna put functional program. I'm gonna show it's the same thing almost. So in Haskell, the way you would do that is you would just do, let's do it this way. F of x would be sum of 0 to x. And if you use the same heuristic then that we chose for the functional or the imperative program, we would say, well, there's one line, so we just takes one step, right? It's easy. But here we're calling a function, so it's not entirely clear what's going on. Like you're actually cheating by calling a function. We called functions here, but they're quite innocuous. It's just adding numbers. That's not too hard. But here we're calling a function that is quite magical because there's everything in one go. And sum is a bit more complicated, but basically the number of steps of sum equal the size of the array that we give it. So if we do f of 5, that's sum from 0, 1, 2, 3, 4, 5, and that is 6 elements, right? So this is actually 6 steps, right? And we can count the entire line as 1 step. So it's 1 step that actually hides 6 steps. So it's 7 steps. Right. Now there's another way to do the same algorithm. Well, sorry. There's another algorithm to fix or to solve the same problem. And if you write this in mathematical notation, you have the following property, that f of x equals x times x plus 1 divided by 2. If you want to try it, from 0 to 5 we had 15, right? So f of 5 would be 5 times 6 divided by 2, and that is 15. How cool is that? I'm not going to prove this right now, actually. I just realized that I haven't proved it. But you can probably imagine that doing one multiplication and one addition is a lot less work than doing, where is it? Than doing 12 additions, right? Well, 5 additions. And so that's what we're going to use. So if you write this as an imperative program, you have f of x is return x times x plus 1 divided by 2. And that's just one line. And the only operations there are division, addition, and multiplication. Those are all the steps. So even if you count those are just 3 steps. And as a functional program, well, you would write it like this. f of x equals x times x plus 1 divided by 2. It's literally the same thing. And if you want it as a manual program, well, you also have 3 steps, right? First one is add 1 to x, then multiply x and step 1, and divide step 2 by 2. So in all cases, we found a better algorithm, an algorithm that takes 3 steps if you really, really want to be like anal about what is a step. But generally, it's just like this one single expression. And so this counts usually as 1 step. There is only one thing to do, and it's this simple mathematical operation. So here's an example of a problem, 2 algorithm, 2 ways of understanding how complex, not complex, but understanding the complexity of it. And the complexity means how many steps it takes to solve. And when people talk about complexity, like the study of complexity, it's the study of how the steps, how the step count changes depending on the input size. So if I have as input 5, this thing takes 1 step. If I have inputs 10, well, the formula doesn't change, right? So it's also 1 step for the new version of the algorithm. If I take the previous version of the algorithm, if I give it input 5, I would have 5 steps. If I give it input 10, I would have 10 steps. If I give it input 100, I would have 100 steps. So the complexity is linear for our naive example, and it's constant for our second guess, for the new one. And there are other ways to understand how complexity evolves. So some algorithm, the number of steps increases with the square of the amount of the size of the input. So for example, if for an input of size 5, it would take 25 steps. But an input of size 10, it would take 1,024 steps. That's exponential, but that's fine. You see what I mean. That's exponential, but that's fine. It blows up, right? And that's what complexity study is. That's why people study algorithms, to understand, is there a way to make the amount of steps smaller, even though we increase the size of the input, even though we increase the size of the problem? And that's why people are really into it. All right, it's 9. I'm going to stop here now. I'm going to continue with this for Friday. We're gonna probably see things like sorting algorithms, because those are the typical example that we give people. I'm gonna do the same thing where we're gonna have like the physical version and the program version, so we can have an intuition of how it actually works when you do the algorithm. All right, see you in a little bit.